Taking over from the previous week, I'll be talking about Cauchy's equation, the Navier-Stokes equation, and a couple of examples based on Navier-Stokes equation. So, Sir has covered boundary layer in the last class of this week, but that I'll be leaving for next week because he has 4 more lectures lined up on boundary layer. So, all of that together I'll do in the next week. So, right now we'll do normal Navier-Stokes equation solving. So, this is a Cauchy momentum equation. Rho capital dv by dt, that is a substantial derivative. I'm writing everything in vectorial notation, okay? So rho g is a vector, p is a scalar, but delta p, gradient of a scalar is a vector, and this is divergence of the stress tensor. So divergence reduces uh, one order, okay? So it's if stress tensor is 2 orders, then dotting that or taking the divergence will reduce one order, that will also become a vector. We also saw that the stress tensor is proportional to the gradient of the velocity vector, right? Example, tau yx is equal to mu into dou vx by dou y. So how does the velocity gradient vector tensor look like? So I'll just represent it in matrix form. I'm not doing x, y, z. I'm just telling that x1, x2, x3. Well, it's understood that x1 is like x and x2 is y direction and x3 is z direction. Okay. And likewise the components, the velocity components 1, 2, 3 suffix, they also are in those directions. So the velocity gradient tensor looks like this. Okay. In index notation, I can write velocity gradient of velocity as this form. I going from 1 to 3, j going from 1 to 3, dou vj by dou xi. And since this is a tensor, there will be two directions associated with it, okay? Ei, ej. Okay. For instance, like tau xx is tau xx, ex, ex. Tau xy is the magnitude of tau xy into ex, ey. Tau xz is tau xz, ex, ez. So why does stress have two directions associated with it? That we already talked about in the previous class, but I still repeat that. So basically, if you see this as y direction, this as x direction, okay, and looking at the 2D planar view, see this is this plate, okay, this profile of the plate is this top plate over here, this bottom plate which is fixed, say, so velocity gradient will appear like this. So obviously this is y direction, this is x direction, so unidirectional flow. So here tau yx, what is tau yx? It's the momentum flux or viscous stress. This represents the rate of momentum transfer per area because this is a flux. Rate of momentum transfer per area. That ties in with the definition of what a flux is. Okay. Flux is something divided by time divided by area. Okay. So rate automatically includes a time component. 1 by t is involved. It's like momentum by time by area. So what does the yx here represent? It represents that momentum transfer is in the y direction. And the velocity, because which drives the stress, is in the x direction. Momentum transfer in y direction and x is the velocity direction. Okay. So basically just note that velocity gradient and momentum transfer are in the same direction. Huh. And just I'll introduce some other concepts also. Okay. This is a normal vector C n1 ex plus n2 ey plus n3 ez. Okay. This is the surface and this is the normal vector direction. So this when you dot it with the stress tensor gives you the stress vector. Okay. So just keep that in mind. We may use it later on. Okay. Another concept here. Any tensor or any quantity, okay. Tensor as we saw, it's in the form of a matrix, okay. So it can also be broken down like this. I'll define all the terms. Wait. Right? So right hand side, if you add, you will get the left hand side because x transpose by 2, they cancel each other. Okay. So in this thing, if you see, so this matrix is a symmetric matrix. And this is an anti-symmetric matrix. What does symmetric mean? What does anti-symmetric mean? Any matrix, okay. If you take the transpose of that matrix and it is the same as the initial matrix, then it is symmetric, okay. So here, if it's x plus x transpose by 2, you transpose this, it is just x transpose plus x by 2. So both are equivalent. What is this term and what you're getting here, both are same. So it is symmetric. Anti-symmetric means that transpose becomes negative of that. For instance, here it is x minus x transpose by 2. If I do the transpose of this, what do you get? X transpose minus x transpose of transpose by 2. Transpose of transpose is just x. Okay. So it reduces to x transpose minus x by 2. And if you see, this is just the negative of this term. settings. Find settings. Okay. Forget it. So basically, this is just a negative of this. Okay. Minus of x minus x transpose by 2. Okay. So transposing of this thing is just a negative, right? So this is anti-symmetric. Likewise, if I take the velocity gradient, that's also tensor. I can represent it in this form. This is one term, this is second term. So as you can clearly see, first is a symmetric part. This I'm representing as gamma. Second, this one is the anti-symmetric part. This I'm representing as omega. So basically our velocity gradient has this symmetric gamma and this anti-symmetric omega. And you must have, if you have gone through Sir's lectures and all, you must have seen that this gamma, this part, the symmetric part, is responsible for deformation in the fluid. I just note it down. And this part, omega, is responsible for rotation. Remember the vorticity concept? So like that, including rigid body rotation. So we will be focusing more on this gamma term. That is what is known as a rate of strain tensor. So our tau stress, the deviatory component of stress is proportional to rate of strain tensor. And it's not a function of omega. Just keep this in mind, okay? Okay. So first half of the class will be mostly doing theory, okay? I'll be giving you breaks in between, but we'll solve problems after I cover this theory part and the boundary conditions, how to apply them, etc. Okay, so what are the types of fluid motion? All types of fluid motion can be broken down of into four parts, okay? Translation, rotation, dilation, and shear. So any kind of fluid motion that you encounter in life, it can be broken down into these parts, these four parts. So like if you superimpose the translation, the rotation, the dilation, and the shear, you can define any practical any fluid. Translation is just like say a pocket of fluid. It's just been translated like this. Rotation means like it's like this. The orientation changes because that's an anti-clockwise rotation. You get this. Dilation means like it expands uniformly in all directions. Okay, so it's like this. Then it becomes like this. So basically, the original of packet of fluid, it has just dilated like this. Okay, it can also happen in the opposite direction. And shear is basically this. Say like there is deformation in the fluid. The case of the two plates, top plate you're moving with some velocity and bottom plate is fixed. So there is some shear associated with it. So only these four types of primary fluid motions, when you uh, combine them in various ratios, you can practically define any fluid. Okay, and we already saw in the previous class that the overall stress tensor, I define it here, sigma, has got two components. One is the isotropic pressure component, and one is the deviatoric stress, tau, which we just now saw, which is proportional to the rate of strain tensor, right? So this is pressure term. And if you remember last class, I told you that pressure is isotropic. So it's isotropic pressure tensor. Isotropic means that it acts with equal magnitude in all directions. Okay, so this is a particular point of fluid. So it doesn't depend on direction. In all directions it's same. That's isotropic pressure. And it's always normal to a surface. That also remember. Say some surface pressure is always normal to it. The same direction as the normal vector. And another thing to remember about pressure is that it is non-zero even when there is no flow. So even in a hydrostatic case, like say I'm just having a beaker, stationary fluid in the beaker, still there will be pressure at each of these points because of the weight of the fluid above it, which we just defined as rho gh, if you remember, hydrostatics. So its isotropic pressure is non-zero even when there is no flow. Given this kind of diagonal matrix form, minus p because it's acting inverse, opposite to the normal vector. Non-diagonal components are zero, only diagonal components are there. Those are all minus p. What is this term? This is the viscous stress tensor. It's a deviatory component. It is not equal to zero only when the material deforms and flows. Okay. Now let us focus a little bit on the viscous stress tensor term. Okay. So let us take the simple example of Newtonian fluids. That is the fluids which obey the Newton's law of viscosity. Tau is proportional to the velocity gradient. Velocity gradient to the power 1. Okay. Constitutive relations for the deviatory component. Right. So it is given as 2 mu into rate of strain tensor minus one third into divergence of velocity identity matrix I'll define all the terms. Just wait. Plus 3k into 1/3 delta V identity matrix. Okay. So the first term over here that you see, this term, this is because of shear or shape deformation. I showed you right over here, four types of fluid motion. We have defined shear. So yeah, because of that, the stress that develops is given like this. 2 mu into rate of strain tensor minus 1/3 divergence of velocity into in the I double cap in I, where tensor is just diagonal matrix. It units one the diagonal like this. Okay. And the second component that you see, which is 3k into this one, this is due to dilation. So I'll define the terms. Mu is dynamic viscosity, which you must be familiar with it, right? This is the viscosity that you get in the Newton's law of viscosity. Tau is equal to mu into dV by dx. K over here, it's the bulk or dilational viscosity. It has to do with compression and expansion. One thing you have to remember that both mu as well as K are not functions of the rate of strain tensor. Fine. So typically what happens over here is that this these two terms which comprise the Tibetoric stress, okay, this is a K component and this is a mu component. So the K, which is a bulk or dilational viscosity, is often much smaller than the dynamic viscosity, okay. So in all practical cases, K is much smaller than mu. So we didn't neglect that part. Tau is just 2 mu into rate of strain tensor minus 1/3 divergence of velocity I. And we already told it is Newtonian. Now we are also saying that it's incompressible. Okay. Meaning del dot V is equal to 0 from the continuity equation if you remember. Right? Refer to the notes of the previous class. So if del dot V is equal to 0, tau is just 2 mu gamma. What is gamma? It's a symmetric part, right? Of the velocity gradient. It's half into delta V plus delta V transpose. 2 gets cancelled. It's just mu into delta V plus delta V transpose. So you substitute for this tau. We took Newtonian case incompressible approximation. So it's you substitute for tau in the Cauchy momentum equation. Okay. The Cauchy momentum equation is given over here. Rho dv by dt is equal to rho g minus 10p plus this term. So this tau you substitute. Okay. So it will look like this. You assume mu is constant. Fine. So there is some mathematics involved in how to simplify this. I'm not going through the details because like for that you need to know some basics about vector and vector algebra. So I'm not going into the details. But if interested, I can give an additional note of it when I upload the file. So I just want to tell you that when you put this into this equation, and after some mathematical manipulation, this Cauchy's equation reduces to this form: rho dv by dt is equal to rho g cap minus gradient of pressure plus mu del square, and this is what is the famous Navier-Stokes equation. Fine, it's valid for incompressible Newtonian fluids. Just this is a very important equation which will be coming through in many examples. Okay, we'll also solve two, three sums problems related to Navier-Stokes equation, and this del P minus rho g. In some books, they define this as they reduce something called dynamic pressure. Okay, in some books, they may define like this. Okay, just for the sake of completion, I'm telling this back. So it reduces to this form. Okay, for Newtonian fluid, I already told that this mu k and all are not functions of the rate of strain tensor. But what happens in a non-Newtonian fluid? It's a much more complicated case now, right? So for a non-Newtonian fluid, we have the power law model. Mu is some index into 2t to the power n minus 1. This 2t is just the magnitude of the rate of strain tensor, okay, gamma. So for Newtonian fluid, what happens? Mu is a constant rate. Mu is independent of the rate of strain tensor. So n is equal to 1 for Newtonian fluid. It is less than 1 for shear thinning fluid. It's greater than 1 for shear thickening fluid. Fine. So basically, rho dv by dt is equal to minus dynamic pressure plus del dot. Here mu is a dependent on the rate of strain tensor. Obviously, we'll have the same. So it's a bit more complicated now. Okay, so I'm just like in case of Navier-Stokes equation, it's not that easy to simplify. Okay, so let's take a small break now, and when I return, I'll explain about boundary conditions and how we apply boundary conditions. So let's take a small break for some time. Next up is boundary conditions. Welcome back. So boundary conditions, an important thing to note about boundary conditions is that they're not from first principles. Or first principles meaning like Newton's laws of motion or something very fundamental in physics. So boundary conditions are based on observations, not from the laws of physics. So there are types of boundary condition. First one is, say there is an interface between two medium, one and two. Say this is water, that is air or something like that. I define the tangential velocity over here as Vt, comma 1 in phase 1. And in phase 2 it is Vt, comma 2. T here is a tangential component of velocity. Fine. So what this first kind of boundary condition says is that there is a continuity of tangential velocity at the interface. So this is the famous no slip condition. Okay. So it's across the interface. It is just the continuity of tangential velocity. Fine. For instance, say this is the surface of a pipe. Some fluid is flowing like this. This is phase 2. Here, if I say the solid is phase 1. So across the interface, that is at the wall between the solid liquid boundary, Vt2 and Vt1. So obviously on Vt1 will be 0 because on this side there is no flow. So Vt2 will be equal to Vt1 is equal to 0. So that's the famous no slip condition. That at the wall you take 0 velocity. And remember, this is just a tangential component of velocity. Tangential to the surface, okay? Normal component will come later. Okay. Say there is some surface, there is some velocity here, and this is the tangential direction. So Vt is just T dot V or V dot T. Okay, because A dot B is equal to B dot A, na? Like that. So this is a famous no slip boundary condition. So this was the tangential velocity component. Now let us consider the normal velocity. So this is phase 1. This is phase 2. So normal velocity here is Vn2. Here it is Vn1. So this is a no penetration condition. So this is a solid. This is some fluid over here. Okay. This fluid can't penetrate to the solid unless it's porous. So for porous, that's a different case. Anyway, this is what is known as no penetration condition. Third is stress balance. Okay. This is medium 2. This is medium 1. Okay. So I already told you that stress vector in some direction. N is the normal vector to that surface. It's just the normal vector dotted with the stress tensor. Fine. So here it is like S2 now because medium 2, S2n. This is S1n. Okay. So generally you would assume that S1n is equal to S2n. That's a stress balance, but it's not that straightforward. Okay. There are some other terms which we may not be using in our case, but just for the sake of completion, I ought to mention that. So basically, this boundary condition, the stress balance condition, is that Sn in medium 1 is equal to Sn in medium 2 at the interface plus delta S gamma plus 2H normal gamma. Okay, so these are two interesting terms that we are mentioning. So this is a bit advanced, like you mostly we won't be using it in this course, but for the sake of completion, I thought I would just tell you this. So what this del S is that it's a del S gamma is a surface gradient of the surface tension. So this is how it is defined. Surface gradient of surface tension. And over here, H is what? It's curvature. Say this is an interface between water and toluene. Toluene like is an organic compound. So you'll have a surface tension associated, right? Between the two phases of toluene and water, in which can be a function of temperature, viscosity, pressure, etc. Okay, coming to the surface gradient term, what is gradient? Gradient we define as dou x of something ex cap plus ey cap dou y plus ez cap dou z. This ex you can write here also, just I'm just telling you. Like if it is del t, it is like dou x of t into ex cap like that. Okay, velocity say. So yeah. So if this is a surface for us in the xy plane, see, this is x, this is y, normal to this, perpendicular to this plane is z. So basically, what is surface tension? Surface tension acts at interface, right? For instance, a drop. Surface tension is a reason why the drop is spherical in shape to minimize the surface area. Fine. So what is surface gradient here? Surface gradient here, if you remove the surface gradient in this case in the xy plane, is just the gradient minus Ez dou z. Okay. So in this case, it is just Ex dou x plus Ey dou y. Okay. So obviously it acts tangential to the surface, right? Because it's in xy. Likewise, this other component that we see, 2h n gamma, it acts normal to the interface. So this is H is what is known as mean curvature because of the curve of the interface. For instance, if the interface is flat like this, we'll just say that H is equal to 0. In this case, say normal is in this direction, H is less than 0. If H is normal is in this direction, H is greater than 0. It's by convention, this sign convention of curvature, it's that indicates that in this case it is like a concave part, so it's greater than 0. It's convex, so it's less than 0 like that. And more curved the surface, higher the curvature. Okay, I'm not going into details about this curvature. Okay, like generally we have two components of two radius for any interface. So it's just 1 by 2 or 1 by R1 plus 1 by R2. Okay. Um, okay, I'm not again going very deep into all this because that's outside the scope of this course. But like we'll have one type of for cylinder, we'll have uh, uh, minus 1 by 2 R curvature. A sphere will have minus 1 by R, etc. Right? Okay. So like cylinder, like there is one. So this associated with this surface, the radius is R, but for here it is like infinity. So it will be like half 1 minus 1 by R minus 1 by infinity. So it's minus 1 by 2R. Okay. For sphere, like it may be minus 1 by R. So I'm not going into details. Just to remember that there is something called a surface tension whenever you're talking about interface, and that has got both a surface gradient component as well as a curvature component. And if the interface is like in this kind of shape, and you define the normal vector like this in this direction, right? So here curvature will be less than zero. Here it will be greater than zero. Okay, like that it will keep on changing. Okay, so what's a complete stress balance? We'll again come back to the boundary condition. So complete stress balance is just n dot sigma tensor. So it's a surface, it's a stress vector that will get at 1 is equal to n dot sigma at 2 plus surface gradient of the surface tension plus this curvature component. So this is the normal direction. And this will be tangential direction. You can always break this as the sigma as the isotropic pressure component and the deviatory component. And again, you can decompose into the normal and tangential components. Like sigma N is equal to minus P plus tau N. Tau N is generally zero, but in case of some non-Newtonian fluid center, you'll have a normal stress component also. So it becomes important there. So obviously there are two ends, like one is the direction of the stress component, another represents the surface orientation. Right, like I'm just defining these terms, not important, just for the sake of completeness. So normal stress balance is minus P plus tau N 1 equal to minus P plus tau N 2 plus 2H comma. So if curvature is zero, that is for flat interface. minus p plus tau nn 1 is equal to minus p plus tau nn 2. And for flat interface with stationary fluid, P1 is equal to P2. For a curved interface with stationary fluid, minus P1 is equal to minus P2 plus 2H comma. P1 minus P2 is equal to minus 2H comma, which is the famous Young Laplace equation. 2H comma is what is known as Laplace pressure, capillary pressure, sorry. For sphere, P1 minus P2 is equal to 2 gamma by R. Like all this, like you can derive all these things very easily, just basic mathematics. I'm not going to do that. So likewise, you can do tangential stress balance also. Tau nt at 1 is equal to tau nt 2 plus t dot ls gamma. This is nothing but n dot sigma dot t. For a fluid that is stationary, surface gradient of surface tension is 0. And there is something called Marangoni flow where this is not equal to 0. Anyway, not going into details. Okay, like there are some examples I have, like calculate pressure inside a water droplet with varying radius, and then we'll see the effect of Laplace pressure and how certain phenomena occur, why it is more important in small scales, like in study of colloids and all. Okay, I'll just leave that because that is not being covered by the class. So I have a book which I'll be uploading here very shortly. Bird Stuart Lightfoot. Okay, I'll be uploading it after this class. So you just have to refer to appendix. If you have time, you go through the chapters. Like they are all related to what we are doing here, like the Cauchy equation, Navier-Stokes equation, etc. If not, just go through appendix B. Okay, appendix B. Like we are like sir has also we went through this form, right? To 2 by 3 mu minus k into del dot v, etc. All these things will be covered in that, like the continuity equation in various coordinates like Cartesian coordinates, spherical coordinates, cylindrical coordinate. Likewise, energy transport equation, the mass diffusion, the species transport equation, the constitutive relations, equation of motion. Then over here in various coordinate systems, and also like the Navier-Stokes equation, which is simplified a case in case of uh, we see here it for a Newtonian incompressible flow, the Navier-Stokes equation, in all the coordinate systems. So if you just refer to this all the time when you're solving problems, okay, and I'll just go through a few sample problems. I won't solve them fully, but I will just give you the final equation, final form. I'll tell you what are assumptions to take, what are the boundary conditions, what's the final form you should get, etc. And if you have any doubt, you just feel free to ask me next time. So before the break, I'll just pose a problem to you and just think about it. And after the break, like we'll see how to solve them. Okay. No attendance, I think today. No attendance. No problem. Okay, some sample problems. So there is an example: flow between two parallel plates due to pressure. Okay, this is Poiseuille's flow. Like there are two parallel plates over here. Say I say this center line is 0, so upper is at cap h, bottom plate is at minus h. Okay, the width of this channel is 2h. So just come up with some assumptions and see what velocity profile you get. Okay, the flow is due to pressure. Okay, okay, just do that. Then we catch up after the break. Thank you. Okay, coming back. So what are the assumptions that you took? First, it is steady state flow that greatly simplifies the Navier-Stokes equation, meaning that dou dot T component is zero. Dou dot T component of something is zero. Second, it is incompressible fluid, like water, say. The continuity equation reduces to this. You can always refer to this appendix P. So if dou rho by dou T is equal to zero, because rho is constant, and this rho also comes out, so it's just del dot V is equal to zero, right? Likewise, you can simplify the equation of motion also. In this case, a Newtonian fluid with constant rho, constant mu, incompressible fluid. So it's like this. What other assumption you can take? You can say it's unidirectional flow. It is only in the x direction that is flow. And fourth is it is fully developed flow. Typically, what happens is that, say some tube is here, okay, through which some liquid is flowing. This radius is r. So only after some length distance, which is known as the entrance length, you get the typical velocity profile. Okay, like this. So basically, the boundary layers are merging in this zone. When I come to boundary layer theory class, maybe class 5, that time, class 4 and class 5, that time we will look at what boundary layer merging means. But the thing is that only after a certain length, that is the entrance length, you get fully developed flow. So we are assuming that we are already in the fully developed flow, okay? So there are some correlations like LV by R is equal to 1 plus 0.1 Reynolds number, where Reynolds number is just rho V uh, U by, no, rho V, yeah, D by mu, rho V D by mu. Okay. So from there you can find the entrance length. Thing is, after the distance LV, we get fully developed flow, meaning that the dou dou component is zero. Velocity doesn't change. Dou u by dou x is equal to zero. Okay. I'm not talking about dou p by dou x or anything, just dou u by dou x is equal to zero after this. So now if you refer to appendix P, okay, appendix B of Burt Stewart Lightfoot. So continuity equation is just del dot V is equal to zero. Here it will be like dou u by dou x plus dou v by dou y plus dou w by dou z is equal to zero. So we have assumed unidirectional flow, so only u component is there. So this is zero, and you get dou u by dou x is equal to zero. So we also got it from the fully developed flow assumption. Likewise, if you simplify the x component of the equation of motion, the Navier-Stokes equation. So I want you to do this as homework, okay? Had you guys been in class, like we have done them together, but since none of you are here, I would just hope for you to do it yourself. Refer to this appendix and do it in your own room or college, wherever. So just observe that, see that whether you get this term from x component of the Navier-Stokes equation. You should get this one, okay? This is constant. So basically, d square Vx by dy square is equal to 1 by mu dp by dx. We are applying a constant pressure gradient. That's what is Poiseuille flow. If there is relative motion between the plates, that is Couette flow. We'll come to that later. So okay, just solve for this. Like if you integrate it twice, you will get uh like Vx is equal to something into y square plus something into y plus some constant. Okay. And what are the boundary conditions? Boundary conditions are the no slip condition that Vx is equal to 0 at y is equal to h. So either at y is equal to h or y is equal to minus h, you do Vx is equal to 0. So that's just one boundary condition. Okay. Likewise, another boundary condition will be dou Vx by dou y is equal to 0 at y is equal to 0 at the center line. At the center line, say we have some velocity profile like this. At the center line, dou Vx by dou y is equal to 0. That is known as the symmetry boundary condition. So you solve this differential equation, you integrate it twice, you apply these boundary conditions and see what velocity profile you get. I'm writing the answer now. See whether you get the same answer, and if you have any doubt, you can ask me in the next class. You will get something like this. Or just raise a question in the forum. If you attend the classes, like we can have discussion face to face, but since you're not here, I would want you to try it. Okay, so this is the velocity profile you have to get. So this is homework, just check it out if you're getting like this. You'll have Vmax at y is equal to 0 is equal to minus 1 by 2 mu dp by dx into h square. And your Vx will be Vmax into 1 minus y square by h square. Okay. And your V average will be defined like this. dx dy minus h2h, that is the total flow rate divided by 2h. Okay. Of course, there is a cross-sectional area term is also here and here. That gets cancelled. So it's just flow rate divided by, yeah, not A, L. Some length scale will be there. That gets cancelled both sides, okay? Anyway, like, just try this out. See whether you're getting 2 by 3 Vmax. This is like part of your homework. And see whether the volumetric flow rate is equal to 4 by 3 Vmax. This also you have to solve. Very simple this question, okay? So I already explained what to do. This is your velocity profile. So just integrate this twice. This equation. This is a constant, okay? So dvx by dy is equal to 1 by mu dp by dx into y plus c1. Then I integrate it twice. It will be y square by 2 plus constant into y plus another constant. Then you apply these two boundary conditions. You will get this velocity profile. From here, like apply the maximum minimum concept and see where the Vmax is. It will be at 0. And this is the Vmax. So you can represent Vx in terms of Vmax. And V average is like total flow rate divided by the cross section area, which is dx dy minus h2h divided by 2h. And you can also find the volumetric flow rate from this, okay? So this is Poiseuille flow. Similar problem you can try out another part of your homework, like immiscible liquids in parallel plate channel. Okay, so these are walls. This is liquid one. Okay, this is liquid two. I define the coordinate system like this. This is x direction, this is y direction. See, this is oil and this is water. Okay, so this has different viscosity, different density than this. This height is h2, this is h1, and this is the interface. Okay, so assumptions I'm already giving you, that is steady state Newtonian fluids, both incompressible fluids, both fully developed flow, unidirectional. It's a 2D problem. It is, forget the direction. It's unidirectional flow. Only in the x direction there is flow. Okay. So based on this, you try to find out, simplify the Navier-Stokes equation. Apply the boundary conditions. Get the velocity profile in both phases. Find Vx1, Vx2. Okay. Tell about the pressure gradient also. So just look at the Navier-Stokes equation, simplify it based on the assumptions. And boundary condition you can apply at H1, at H2, right? The no slip boundary condition at the two walls. Likewise, at there'll be continuity of velocity at this y is equal to 0, and also tangential stress balance at this point. And okay. So I'm giving you the hint here. Okay. What are the hints? Vy is equal to 0. And when you're talking about the x component of the equation of motion, it is just mu I into rho square Vxi by 2y square is equal to 2 pdi by 2x. This is a function of x. This is a function of y, because Vx is a function of y. To get the velocity profile for each phase Vxi. There will be two boundary conditions for each liquid. Okay, that is Vx1 is equal to 0 at h1. Vx2 is equal to 0 at h2. At y is equal to 0, Vx1 is equal to Vx2. And also tangential stress balance. So just try this out. This is a governing equation and these are the boundary conditions. I'll tell you the answer in the next class. Be very big. Just basic mathematical manipulation. Okay. So that is a next class will be solving what is known as Couette flow. Okay. I'll start the next class by solving the Couette flow problem. It has got many practical applications. Okay. So Poisson flow was due to applied pressure. This is not due to applied pressure. It is due to motion of an object. Tangential moment of solid surface. So like next class we'll be solving this problem of two coaxial cylinder. Okay. Like coaxial means like sharing the same axis. The outer cylinder moves at some angular velocity. The inner one is stationary, and because of which there is a velocity profile over here. Okay. So we'll be solving this problem. I'll tell you more about this next class. Okay. So for the moment, like we'll call it a day today. It's already almost 9 o'clock. So yeah, just give this problem a shot. If you can, fine. If you can't, at least you should get this part. This governing equation and boundary conditions you should get for both. This problem as well as the first problem. Fine. And after that, it's just basic maths. So next class we'll start by doing the fluid flow problem. And then I'll shift to boundary layer theory. Okay. Okay, thanks.